All right, let's dive into something that drives us all completely nuts. We're going to solve a mystery I call the full bars paradox. You know exactly what I'm talking about. You've got a perfect signal, but your phone is, well, it's pretty much useless. Let's break down why that happens. So picture it. You're at a concert, maybe a big game, you're in a huge crowd. You pull out your phone to send that perfect photo, and nothing. It just won't send. But you look up at the corner of your screen and you see five perfect, beautiful bars of signal staring back at you. So, what is going on? Why is your phone letting you down when it's telling you everything should be great? Well, the answer is all about shifting how you think about the problem. See, it's not that your phone can't see the cell tower, it can see it just fine. The real problem is that thousands of other phones are all screaming to talk to that same exact tower at the exact same time. It's not a signal strength problem at all. It's a massive digital traffic jam. To really get this, we have to stop thinking about signal bars and start thinking about something called network capacity. And honestly, the best way to picture this is to imagine the whole mobile network as this huge invisible highway system just floating in the sky above us. And this, right here, is the key to the whole thing. Your signal bars, all they tell you is, can I see the highway? That's it. It says absolutely nothing about the highway itself. Network capacity. Now that's the real question. It asks, how many lanes does that highway have? Because, if 10,000 cars all try to get onto a tiny 2-lane road at the same time, it doesn't matter how great their view is, nobody's going anywhere fast. So if it's really a traffic problem, how do engineers even begin to measure and manage this invisible gridlock? Well, it turns out they have very specific tools and units just for counting all those digital cars on their invisible highway. And what's really cool is the main unit they use for voice calls. It's called an Erlang. Sounds a little funny, I know, but the idea is actually super simple. One Erlang is just one phone line being used totally maxed out for a solid hour. It's the basic building block for figuring out how much talking is happening on the network. Now, here's a little industry secret for you. Networks are actually designed to fail sometimes. Yep, they can't possibly build a highway big enough for every single person to make a call at once. It'd be way too expensive. So they define something called a grade of service, or GOS. This is basically the percentage of calls that they're okay with blocking during the busiest hour. It's the network's way of putting up a sign that says, sorry, on-ramp's closed, try again later. For instance, here in North America, a typical grade of service is about 2%. That means the engineers are designing the system knowing full well that during that peak rush hour, 2 out of every 100 people who try to make a call might get a busy signal. It's this calculated trade-off between keeping costs down and keeping users happy. So how do they figure all this out? They use this amazing tool called the Erlang B table. It looks intense, but it's basically the master cheat sheet. An engineer can look at this and say, okay, I've got 7 lanes or circuits, and I'm willing to accept a 2% blockage rate. The table then tells them, great, that setup can handle exactly 2.94 Erlangs of traffic. This is how they turn all that theory into real-world hardware. But wait, that's all for voice calls. What about data? Streaming a video, loading a website. For that, it's not just a simple yes or no question of being blocked. It's all about the quality of your connection. We call this quality of service, or QoS. Think of this as the highway's traffic rules. Are you in the slow lane or the express lane? What's the speed limit? These are the things your phone and the network are constantly negotiating, totally behind the scenes. They're making a deal on things like minimum speed, maximum delay, even how many little bits of data it's okay to lose along the way. All of this adds up to determine whether your video plays perfectly or you get stuck with that dreaded spinning wheel of buffering. Okay, so we've got this highway with a certain number of lanes, but what happens when it really truly hits its breaking point? Well, it turns out there are actually 2 totally different ways a network can fail. First up, there's the hard limit. This one's easy. It's the absolute physical number of connections the hardware can handle. It's like the number of lanes on a bridge. You literally just can't fit any more cars. But then there's the soft limit. And this is the sneaky one. This is when so many people are using the network that they all start creating interference for each other and everyone's speed just grinds to a halt. It's not that the bridge is closed, it's that you're in a total gridlock traffic jam. I think this is the best analogy for it ever. The hard limit of this power strip is the number of outlets. You can't plug in more things than you have holes for. But the soft limit, that's what happens when you plug in a space heater, a microwave, and a hairdryer all at once. They create too much electrical interference, and bam, the circuit breaker trips, shutting everything down, even if you still have empty outlets. So, And this is the crucial part. Engineers have to plan for both of these limits. In a real-world example from their planning docs, the hardware might have a hard limit of 55 users at a time. But because of all that radio interference, the soft limit kicks in at just 22 users. So the network's true capacity is always, always the smaller number. The traffic jam happens long before the bridge is even full. Okay, so let's bring it all back to that stadium. Now that we're armed with all this knowledge, how do engineers actually build a network that can handle 70,000 people all trying to post selfies at the exact same moment? Well, they have a master plan. It's basically a four-step process. First, they estimate the traffic. How many people are going to be there and what will they be doing? Calling, texting, streaming video. Second, they define the service level they want to provide. Is a 2% call block rate okay? What's the bare minimum data speed we need to deliver? Third, they whip out those Erlang cables and do the math to figure out exactly how many lanes they're going to need. And finally, they design the actual system, making sure it respects that super important soft limit, the point where everything grinds to a halt. When you really step back and think about it, it is just this massive, incredible, invisible balancing act. It's this constant dance between physics, statistics, and economics, all happening in milliseconds, just so you can send a text from a crowded place. It's kind of mind-blowing. So the next time you're in a packed stadium and your phone actually works perfectly, just take a second. You'll know now it's not magic, it's a masterpiece of invisible traffic planning. And it kind of makes you wonder, doesn't it? What other huge invisible systems like this are just quietly humming along in the background, making our whole modern world possible?